right, example 4. Find all real solutions to the equation 2x to the 5th plus 6x cubed plus 3 equals 3x to the 4th plus 8x squared. So the first thing we have to do before we can use the rational roots theorem is we have to put this in general form first. In general form. Also, I want you to notice that the question this time is worded differently. It doesn't say find the zeros, it says find the solutions. And notice instead of having a polynomial function, p of x equals whatever, or f of x equals whatever, we have an equation with an equal sign in it. And so we're finding the solutions, but guess what? Solutions are still zeros, as long as we have our entire equation on one side equal to 0 on the other side. So the first thing I want to do is go ahead and put that in order from highest exponent to lowest exponents. While I'm at it and I'm paying attention to the exponents, I'm actually going to slip in a 0x there so that I don't forget that we're missing our linear term with x to the first power, basically. So then that equation is equal to 0 because I moved everything over, and all that's left on the other side is 0. Make sure I change the signs on the ones I moved over. They look good to me. I think I'm good. All right, now we're going to do the rational roots theorem, which is factors of 3, so 3 and 1, over factors of 2, so 2 and 1, because our constant term is 3 and our leading coefficient is 2. Constant over leading coefficient. So that gives us the same possibilities we had in example 1 and 2. I might be writing them in a different order, but it's all the same ones. So just to find these possibilities, I'm taking every number in the numerator that are all the factors of the constant, and I'm dividing by all of the possibilities in the denominator, which are all of the factors of the leading coefficient. So we have 3 halves, 3 over 1, 1 half, 1 over 1, and positive or negative possibilities for all of those. Okay, so those are our potential rationals. I can't spell potential. Potential rationals. Now we're going to use synthetic division to figure out which ones are our actual solutions or actual zeros. Okay. So choose one of the 8 possibilities. We can choose whichever one you want to. I usually like to start with 1 and -1, but you don't have to. And we saw a failure of that in our last problem when I decided to try 8 first. That doesn't mean 8 wouldn't ever work, but it just didn't in that situation. So because I like to start with the easy ones first and save the hard ones for later, just because you might not even have to use them, I'm going to go ahead with 1. So 2, -3, 6, -8, 0, 3. See, and I kind of like the fact that when I rewrote this, I put that 0 in there, so then I didn't have to stop and think about it when I was writing it out for my division. Bring down the 2. 2 times 1 is 2. -3 plus 2 is -1. -1 times 1 is -1. 6 minus 1 is 5. 5 times 1 is 5. -8 plus 5 is -3. -3 times 1 is -3. 0 plus -3 is -3. -3 times 1 is -3. And 3 plus -3 is 0. So we started with a 5th degree polynomial and 1 divided into that. So that means we have now a 4th degree polynomial. And since the first one we tried worked, that means we still have 8 possibilities because the 1 could work again if we wanted to try it again. Do we want to try it again or do we want to try something else? You think we should try it again? Okay. We might have previewed this problem to get an idea of what worked, but just keep in mind that if you don't know what works, well, I'm actually going to tell you a little cheater thing you can do. You can use Desmos, and you can graph the function and see where the x-intercepts are. And that tells you which ones of your rational roots, your rational zeros, potential rational zeros, are actual rational zeros. And then you divide with those. Now, this little cheat is just to help save you time on homework. It's not going to help you on a test because you can't use the graphing technology on a test. So the idea would be behind saving you time on homework, where you actually understand that if you had to try all 8, it's going to take you some time, and some will work and some won't. And you're willing to spend that time on a test to get it right when you can't use the technology. But I know we have busy lives, and saving a little bit of time here and there is always valuable. So that's where technology becomes very helpful. Okay, so we can go ahead and do my division. And I'm ignoring that last 0 because that was the remainder from the last problem, so it's not actually part of the new polynomial. And it worked again, so good, I got 1 twice. Technically that means it's a 0 of 1 with a multiplicity of 2. But we aren't finding zeros, we are finding the solutions, and we don't care if a solution happens twice, it's still just one solution. So far, we know that 1 is a solution to this equation. There might be more, we should keep going, there could be up to 5, although right now, since we know we have 1 that's repeated, we know we're not going to have more than 4 solutions because this one's repeated. So that is part of our 5. All right, let's try something else. We could try -1, we could try 3, we could try -3. We could jump into a fraction and give that a try. What do we think? What should we try? Should we give one of the fractions a try? I honestly don't remember if this is one of the answers or not, but I think it might have been, and if it's not, it was a -1/2. So we'll try this one. If it doesn't work, we'll do the negative. Fact that, I don't know, let's see. I'm thinking since our answer here is all positives, if the 0 is positive, then the numbers are just going to keep getting bigger. So it's not a bad idea to have it not work, though. It's good to have an example of that. So 1/2 is 1, and that brings us to 2, which takes us to 1, which takes us to 7. This is starting to look not working. Nope, that one didn't work. So now I'm going to go with the -1/2, but I'm just going to go back to that step we just had. So go back to these numbers right here. Okay, so bring down the 2. 2 times -1 is -1, gives us a 0. 6, -3, 0. At this point, we have a quadratic, and instead of trying more problems, it's usually best to just stop with your quadratic. So 2x squared plus 6 is what we have left. And technically, we're solving this equation, so go ahead and set it equal to 0 if you want, even though that 0 is not why I set this equal to 0. That 0 is the remainder. I set it equal to 0 because we're solving the equation, and even if we were just finding zeros, it would still be that same process. All right, I'm going to go ahead now and solve this problem here. We could try factoring it, but it's not going to factor because we could factor out a 2, and then we would have x squared plus 3, and that doesn't factor. We probably just want to move our 3 over to the other side and solve it from that. So you could either do this with the whole leftover thing equals 0 and move over the 6 to the other side. I guess that would be a 2. And then divide out the 2. That takes us to this point here, so that 2 didn't even really matter, right? When we factored out the 2, we don't do anything with the 2 to help us find the solution because the 2 would just divide out. So now our answer comes from doing plus or minus the square root of -3. Now, what do you know about that? That is not a real solution. If we were in section 2.5 right now, we would finish this problem and we would say, oh, guess what? There are two complex solutions, plus or minus I square root 3. So we have actually two imaginary or complex solutions. Usually we call them complex. Complex solutions. But they're not real. So do we care about them in this particular problem? No, we don't. So the solutions then to this particular polynomial equation are 1 and -1/2, because those are the ones that worked with synthetic division. Those are the ones that weren't imaginary. And we don't need to worry about multiplicity or repeats. It's either a solution or it isn't. So that's it.